Alright, in this video we're looking at section 4.2 and 4.3. We're particularly going to focus on the function f prime and what this says, what f prime says about the function f. Okay, so I'm making an assumption. An assumption in this video is that you can do all the derivative properties to find f prime from the function f. What we're going to do in this video is we're going to focus on, once you can find f prime, if f prime is known, what we need to do is to interpret what's going on with f prime to tell us about the function f. Okay? And one key definition that's going to be important in this section is the definition of a critical point. So a critical point of, in this case we'll say it's a critical point of the function f of x, is a value of x for which the derivative of the function, so the derivative of this function, right, that you've been given, is equal to 0 or does not exist. Okay, so this is an important idea, a critical point of a function f of x. Okay, so let's look at an example or a critical number or a critical point. Okay, and so here's the definition from our textbook. Okay, and I just want to do a quick example. Right, here is a function f of x. Okay, and as I've made assumptions in this section, I'm assuming that you can use the power rule and whatever derivative properties you need to find that the derivative is equal to this. Okay, now we're trying to find a critical number of this function, and so we need to figure out, when does this function equal to 0 and when does this derivative function not exist. Okay, so if we look at f prime of x and ask the question, is that ever equal to 0? That's the same thing as saying, is 3x squared minus 12x plus 9, does that ever equal to 0? We can see that 3 might factor out of these equations. Okay, so we can factor out a 3. And now we're asking the question, does x squared minus 4x plus 3 equal to 0? And I'm asking, I think that looks like it factors as x minus 3, x minus 1 is equal to 0. And so we can see here that when x is equal to 3 or when x is equal to 1, that is when f prime of x is equal to 0. Okay, so x is equal to 3 or x is equal to 1, those are our critical numbers. Okay, and since there are no places f prime of x never does not exist, there's no place where this derivative does not exist. There's no place where we get a division by 0 or the square root of a negative or something like that. So these are, x equal 3 and x equal 1 are our only critical values. Okay, so if I bring in a graph of this problem, okay, let me bring in a graph here. Okay. Here is the function x cubed minus 6x squared plus 9x plus 2, as promised. And we looked at the first derivative, and we can see here that the first derivative is this graph, and it does cross 0. The derivative is equal to 0 at 1. Okay, and we know that what that means is that at 1, the tangent line has a slope of 0. Okay, so if I were looking at the rise over run, if we zoom out, we can see that the derivative at 1 is equal to 0. There is another place, value of x, where the derivative is equal to 0. Right? The derivative is negative here. You can see the red dot being below the axis. And when x is equal to 3, we have another place where the derivative is equal to 0 again. Okay, so this function has two critical values. Okay. Let's look at another example. Right, the sine of x function. Okay. And for sine of x, we know that the derivative is equal to cosine of x. The cosine of x is equal to 0 from the unit circle. The cosine is equal to 0 at one of or two of these 4 points. Here's the unit circle. Cosine is the x value, so the cosine is equal to 0 at this point and this point, so x is equal to pi over 2 and x is equal to 3 pi over 2. Okay, so there are your two critical values, but cosine has an infinite number of critical values every pi over 2. So every pi over 2, you're going to keep getting 2 pi multiples of pi over 2 or 3 pi over 2. So if we look at the cosine graph, okay, cosine of X graph, okay, we can see and zoom out on this thing. Right? We can see that the cosine is the derivative. There is I'm sorry, I'm looking at the sine graph, no wonder. Sorry, the function was the sine function. It's very important to make sure I have the right function here. Okay, so if we zoom out, there's the sine graph. The derivative is the cosine graph. And we can see here that we're looking for when the red graph crosses the x-axis, when the derivative is equal to 0. We can see that on our blue graph, which is the function, the tangent line levels out and is 0. And the red graph crosses the x-axis. So that's pi over 2, about 3 divided by 2. So it's a number less than 2, but, bigger than a half, but less than 2. And then we have another critical value. Let's see, the derivative goes negative here. And because the derivative is negative, this function is sloping downward. So when the derivative is negative, the tangent line is sloping downward. And then at 3 pi over 2, this value right here, here's 3 pi over 2. Okay. The derivative was 0 again. It's kind of hard to get that exactly right. So sorry, you can see right between there, the derivative will be flattened out. And then because the sine graph and the cosine graph are cyclical in nature, every this point right here, pi over 2, okay, and then let's go about 6 steps away from that, and you will be over here, right there. You'll be back at another place where the derivative is 0. So every 2 pi multiples of pi over 2 and 3 pi over 2. So one way to write that would be you would have critical values at pi over 2 plus 2 pi times some constant k, where k is an integer. And you could say x is equal to 3 pi over 2 plus 2 pi multiples of 3 pi over 2. Okay. So that's a quick video on what it means to be a critical value. You need to look at when the derivative of the function is equal to 0 or does not exist. And there are a couple more examples to try here.